4.2 Mean Value Theorem. We'll be looking at what the mean value theorem states, its physical interpretation, and increasing and decreasing functions. Essential question: how does the mean value theorem connect average rate of change with instantaneous rate of change? Let's take a look at Rolle's theorem, which is a special case of the mean value theorem. It says, let f be a function that satisfies the following three hypotheses. 1. F is continuous. F is continuous on the closed interval. F is differentiable on the open interval, and that's because we can't find a derivative at an endpoint, so that's why we have to have an open interval. F of A is equal to F of B, so there's two y coordinates that are equal to each other, and therefore there must be a number C in the interval such that F prime of C is equal to 0. And remember, that represents instantaneous rate of change. So in this particular problem, F of A is equal to 0, F of B is equal to 0. So if I were to find the slope between these two lines, right, these 2 points right here, I would get 0. And so what the theorem is saying that is, as long as these criteria hold true, then there's going to be some point in the interval at which the instantaneous rate is equal to the average rate of change, which kind of makes sense because the tangent lines here are going to be positive. The tangent lines here, their slopes are going to be negative, so to go from positive to negative, you would have to have a 0. Now, you don't have to be touching the x-axis. Let's take a look at this situation. F of A and F of B are equal to each other. Notice they're on the same horizontal line. That's going to create a slope that's going to be equal to 0. Similar to this, we have an increasing tangent line slopes, decreasing here, so somewhere in between will be where the instantaneous rate of change is equal to 0. Okay, let's take a look at the graphical interpretation. Here, this is not what we just saw before. Notice the A and the B are not equal to each other, but that's okay. We can still find a slope between these 2 points. And once we find the slope, we're going to be able to find an instantaneous rate of change that is equal to this slope. So we're saying that the instantaneous rate of change is going to be equal to the average rate of change. Now, the mean value theorem says you're going to find at least one C. Now, there's sometimes more than one C. The mean value theorem doesn't tell you how to find all of them. It just says there's at least one. And so in this case, you see the average rate of change, which is the blue line. This is the average rate of change here. And there's going to be more than one instantaneous rate of change that'll equal that same slope. Okay, here's what the mean value theorem says. Look at its differences, compare and contrast what it says with Rolle's theorem. We still have this continuous on the closed interval. We still have the differentiability on the open interval. And we still have this instantaneous rate of change is equal to the average rate of change. We can also rewrite this equation and make it look like this by bringing this binomial over to the other side. Okay, let's go ahead and do a problem. I kind of started it out and then we're going to go ahead and finish. So I know in the mean value theorem I really do need to know the derivative. So I took the function and found its derivative and evaluated at C. And I also needed to find f of b and f of a, which are these points right here, the y coordinates at the endpoints. And I have put 2 in and I put 0 in. So now I'm ready to use the mean value theorem. So f prime of c, which I already have, is 2c, is equal to, and f of 2 is the number 4, take away f of a, which is 0, all over 2 minus 0. So 2c is equal to 2, therefore c is equal to 1. So this is the location, this is the x-coordinate, and it's located right here. It's in the interval where the instantaneous rate of change is equal to the average rate of change. Why doesn't the mean value theorem apply in these two cases? So if I were to draw a average rate of change, that would be a horizontal line. You can see we cannot find an instantaneous rate of change that is equal to 0. And why is this not happening? Because this is not differentiable in the open interval. Not differentiable. You have to apply the two criteria there. Now in this case, if I were to join the endpoints right here, this would be the average rate of change. And the question is, can we find an instantaneous rate of change? Well, we could, but the mean value theorem only guarantees that's going to happen as long as this is not this is continuous. And since this is not continuous, there is not a guarantee. It may or may not happen, just not a guarantee. All right, let's take a look at, they want us to find the average rate of change from here to here, from -1 to 1, and they want us to find a secant, a tangent of f that is parallel to the secant. So I'm going to use the mean value theorem, which is right here. I'm going to use the function, find its derivative, it's right here. I'm going to substitute c in there. And now I have figured out what f of 1 and f of -1 are, so I'm going to be able to put them into my mean value theorem. So this is a negative c all over root 1 minus c squared, and f of b and f of a are both the same, so this is really Rolle's theorem, and then this is 1 take away -1. So this is actually equal to 0. And if I go ahead and cross multiply, I'm going to get negative c is equal to 0. So c is equal to 0. So that's that one point that the mean value theorem guarantees, and it's occurring right here, where the average rate of change is 0, and the instantaneous rate is 0 right here, and the average rate of change is 0 as well. Okay, so the MVT in real life. Remember that the physical interpretation is that this represents the average rate of change, this represents the instantaneous rate of change, and we're looking to set these two equal as long as we have continuity and differentiability. Okay, if policewoman Betsy sees me at a corner in Minneapolis at noon, and then her husband policeman Bubba sees me 60 miles away at the corner, another corner, at precisely 1 p.m., can they give me a speeding ticket? So we know that we've traveled in 1 hour 60 miles, so the average speed is 60 miles per hour. And because the way we drive, we know that we're going to have a continuous function, time is not going to stop, and we know that physically we can't jump around on, and change one distance to the other. We have to work up through the different distances. So we know that there's going to be some point at which the instantaneous rate of change is equal to the average rate of change, because we have satisfied the mean value theorem. So if the speed limit is 55 or 45 from this location to this location, then yes, we're going to get a speeding ticket. Okay, let's remember what increasing and decreasing functions are. So this is an example of increasing in the interval between x of 1 and x of 2, and that's because this y-coordinate and this y-coordinate, if I compare f of x of 2, it is higher than f of x of 1. So we call that an increasing function. Now over here, f of x of 1 and then f of x of 2, notice that this is lower. When this is less than this one, we call that decreasing. That's not calculus, that's just the definition of increasing and decreasing. Now, how's the mean value theorem going to help us with identifying increasing and decreasing? And here's how it is. Here's the mean value theorem right here. And I'm going to rewrite it. And because x of 2 is always greater than x of 1, I know this quantity is always positive. So then these two quantities have to be the same. So if the y value is less and we have a negative here, then in order for a negative quantity to equal a negative quantity, this will also have to be negative. So the association of a derivative with increasing and decreasing is tied up here, right here. These two will have to be the same. They'll either be both negative or both positive. So if the derivative is negative, then that means it's decreasing because this f is lower than this f. And then I can change and say if these two are positive here, then if the derivative is positive, then that means this y value is bigger than this y value, and it's increasing. So the mean value theorem ties together this idea of increasing and decreasing with calculus. Okay, here's our last problem. We have a function and we want to determine whether it's increasing and decreasing. Now normally you would have had to graph this and take a look at where you saw the y's getting bigger and getting smaller. We don't need to do that with calculus. What we're going to do is we're going to take the derivative and we're going to set the derivative equal to 0 because that's kind of our boundaries. Things change when the derivative is equal to 0. So I set the derivative equal to 0 and solve. And this is a little number line for the first derivative. And I have marked where what x values is a derivative equal to 0. Okay, now what I want to do is I want to check out -2. And when I check out -2, the answer is positive. So the derivative is positive, which means it is increasing. So I put a plus. Now I know everything here is positive because if it wasn't positive, I would have had gone through a 0, and I've already found all my zeros on my derivative. I'm going to check out 0, which is somewhere in between, and I see it's negative. Negative derivative means that it is decreasing, so I put a minus sign. And then I'm going to check out 2, and notice I got a positive right here. So now I know when it's positive, negative, and positive, and now I can make my conclusion. So f of x is increasing when the derivative is positive, so it'll be negative infinity to -2 root 3, and we're going to put a bracket there because we can include that point. And the other interval is over here, so we're going to put bracket 2 over root 3 comma infinity. So this interval and this interval are increasing. F of x is decreasing when the derivative is negative, and that'll be bracket -2 over root 3 comma 2 over root 3. And this ties into the derivative.